So hello everyone, I am Shailesh Mishra and this is my master's thesis defense talk. The talk is about inflection of sign language manuals and non-manuals of the body via rigid geometrical transformation. So let's start by focusing on the main part of our talk, which is sign language, right? So we start with question, what is sign language? I will, if you think about it, the first thing probably that comes to your imagination is hand movements. Now I'll play a video here. Please take your time and feel free to notice the video. So what you have noticed in the video is hand motion because that's obvious. But there are more than that. There are body movements, there are eye facial movements, and there are also different gestures which are not as apparent to us as they are to signing people. And next is another video where an editor of a journal is introducing his journal to the audience. And you can see the amount of expressiveness that is present in his face and in his body. So this is what sign language is. It has a very high fidelity motion and they are very precise about it because it's literally that they are speaking a different language. Now, I'll introduce you to the concept of inflection. So in our language, what we do is we have words, multiple words, which we put together to form a sentence, such as this, the person go home. Here, you will never know if the person is going home, if the person went home, or if the person is going home at the moment. Now, if you want to inflect the verb, we will get a sentence like this, the person is going home. Now we'll understand that the person is going home now or present in the present tense, right? Likewise, the sign language also needs inflection. And to do that, uh, what we have is a sign in a dictionary form, okay? So if you see it from all the angles, what you can notice is the motion is the same. It's being pointed in the same direction, right? But if I want to point it to different directions in the space, I would have to inflect this sign. And to do that, I can simply allow it to inflect using some computations, right? See, now the same sign is being used to point different direction. And this is the idea of inflection. Now, the question is, do you need it? For example, if you want to contextualize some signs in different situations, such as if you want to sit in a screen, small screen, or if you want to exaggerate the motion, and if you just want to be like a normal emphasis on the motion, then what you need is something like that. So you can see there are like same sign being played in three different contexts. Now, this leads us to the question, right? So, why are current system built like this? Up on the, I don't know how, in your screen right there, just above the original sentence, there is how this recording is done. So, a person is in a motion capture shoot and the sign is being recorded, right? It's a sentence, it's a full sentence, which is being going to be played. And if I play back the sentence, you can notice the fidelity is same as the original sentence, right? However, on your left, right, you have this sign which is composed of multiple different sentences. So this is where our motivation comes because this multiple different sentences, which is being shown on the top left corner, that is the original animation or in the gloss form, okay? This is the citation form. And what we have to do is you can see the difference between the citation form and the original sentence. So we want to change our citation form into the original sentence so that they match, right, how a person in a real life would perform. And this is the central part of our thesis is how do we compute this from how we would change the motion capture data from the original sentence into the original. The reason why we want to do that is if we want to create this original sentence, we need to compute the sign needed to create this original sentence. So this is a full pipeline. And what we are going to focus is in the computational part. So now again, now question is, why is it difficult, right? Why is it difficult? The reason is a motion capture data is simply hard to modify. If you want to modify it, you have to manually change each keyframes, and it's really expensive to do so. Next it is impossible to capture for all possible combination of inflections. Like if you want to do it for like point it in 16 directions, then you have to capture it in 16 different ways. And it just gets expensive if you do it for all different glosses, right? So what can we do? Okay, so what have people tried? So you can do something very manual, such as this one, right? Where you hire an artist and the artist will do all the signing motion for you. But yes, this is expensive. Or you can do something such as this, where you have a certain set of scripts, and we generate the signing, right? You can inflect here, but you need an expert person who knows how to manipulate the script, who knows every nuances of the sign language, so that they can create those kind of animations. Still, the animation looks robotic. Next, we have this another completely different idea where we do not care about any of these feature modeling or anything, and we do end-to-end deep learning system. So, for example, we can go directly from text to video, or we can go from glosses to signing motion. Now, the problem with these things is that they are very hard to control, right? And if you look into this figure over here, what you can notice is the head motion is different compared to the one in the original sentence. Now, if you want to modify that, it will take a lot of time. And we go back to the same problem where motion capture data are hard to modify, right? Then we have some other ideas where we compose different motion element from different signs and then compose it together to form a high fidelity motion, like this one. Here, the problem is you have to divide a gloss into different sub glosses and identify each animation of body part to those sub glosses. And this is a very challenging problem on its own. Okay. And then there are other approaches such as this vector-based method, where you would give a sentence and you ask the machine learning model to predict the inflection point. So how they do is, so we have here, now in the next frame they will predict here or here or here or here. And if you see the video, it looks something like this, right? Yeah, it's interesting. Next, we have these prosody-based methods where you insert timing information in the sign language. So like how we speak, we have pauses, we have commas, we have large vowels, right? These prosody-based methods, they also input those kind of timing information into the signing animation. And just by inserting this timing animation, the animation feels more natural now, right? Next, we have something such as this one, which is a theoretical concept behind inflection, and they are rather focused on the intensity of the inflection and how you inflect the words, right? And and since I couldn't find any video for this slide, I just have the photo from their paper, and that's about it. So we are done with the state of the art. Now we want to get into our contribution. So what is our contribution, right? We are going to focus on creating a system that augments the motion capture system. That is, we want to increment the motion capture based system. And how are we going to do that? It's simple, by introducing something called as inflection parameters. So I already motivated that we have a sign, right? In this case, we have some example of index, which we want to contextualize. And then how we do is we have the animation data for the original sign, right? And we want to transform that sign, right? We want to transform that original animation data so that we can contextualize it. And we achieve that using our functions. And these functions have certain parameters, which we call as inflection parameters. So by definition, it's the parameters of a function that transform animation data of a sign to contextualize it. Next, we have divided this whole inflections into multiple categories. And the table is not important. Please do not focus on that. What is important is that we are only focusing on the skeletal animation because we didn't have the data for the facial motion. So we want to focus on the inflection of a whole full body motion. And this is the table summarized into a tree diagram now, and it's very simple to catch. So you have inflections, and then you have something like this. So you have a skeletal animation, which are manual and non-manuals. So manual motions are something like you do it intentionally, and once you do it intentionally, it's like very apparent to then the non-manuals, which are the result of your manual motions, right? And the manual motions we categorized it further into into two parts, which are trajectory and wrist rotation. So trajectory concerns about the hand motion. So you move your hand, right? And the wrist rotation consists of palm rotation, like that. So you're in the 3D space. Then we have non-manuals, which are just small relative transformations applied to different bones in the body. And we apply this transformation to torso, to shoulders, to head, and to the eye gaze. Finally, we have something such as morphological, which are facial animations. And then we also have something that is temporal, which are just control the speed and acceleration of the animation. The thing is, we do not focus on those, so that's why we are just focusing on skeletal.
Question.
Mm.
So there is no inflection on finger.
Yes, right now we don't have that one. Yes.
So is it or is it not?
No, we don't have that
You
one.
don't have. Does it exist or not?
Yes, it exists. Okay. Next, input data, right? So what happens here is we have a motion capture and we want to find the parameters that allow the inflections, right? And you can see the data in the dictionary or in the citation form is different from the one in the sentence. So we have to compute this difference, right? And how are we going to do that? Is we want to do something like distance, like minimization. So we want to minimize the distance between two trajectories. So right now there is one target. So you have here 0 because this is one target. And we want to use L2 norm, which is a distance function, right? And so for example, if I introduce another curve and say we just have only one parameter, which is the rotation parameter here. And if we minimize the error, what happens is as we approach the original sign, the error reduces. So our goal is to get to the lowest error, right? And so basically this is the idea. Of course, the curve didn't match because that's the reality. Like in reality too, we have different curves for our signing motions. And the idea is simple. Next, what we want to do is we want to also compute those relative transformations. For example, the rotation delta and the translation delta. And to compute the rotation delta, what we have is we have certain some say some arbitrary position like that, which is rotated vertically down. Then we have another position, same, but the rotation starts at a different point. Say it starts from here to here. So we want to change this rotation to this rotation. And how do we do that is we compute the mean, right? And we compute the mean for other, then we compute the differences and we apply the differences to the green line. And if you do that, what we get is the same rotation, right? And this is another inflection. And finally, we have this translation offset. The idea is similar to the rotation. We use we have a sign that means that's translated, and then we have this another sign which is further being translated, right? So our goal is to match the green one to the red one, so that we can match the distance like where it originates from. And if we do the same process where we compute the mean and apply the distance, we get the result such as this. And here is how we compute it. The computation is completely offline, which is different pipeline than the visualization, right? And the computation, we have divided into for shoulder, torso, and head parameters. So for the shoulders, here what you can notice is that I have highlighted the spine bone and the clavicles. The value for the trajectory value for the shoulder is relative to the spine. And we use some distance formula to compute the relative offset. And as for head motion, again, the motion are relative to the spine. And finally, we have torso. And in torso, you can notice here that it's relative to the pelvis bone. So that we apply or compute all the like trajectory as well as the rotation is relative to this pelvis bone. Okay. And now for the hand orientation, simple. We just compute the mean rotation, which I have already explained before. And for the trajectory, what we have is we have these 9 parameters we have to optimize, and we use optimizer function so that we minimize all these parameters based on the altitude distance, which I've already given you the example. Okay, so conceptually, this is our idea behind the system. Now, what happens is all these things are computed offline, right? and we store that into a form of into a database. Now, during production, what we need is an online sentence generator. And this online sentence generator is completely different from the computation part. Okay. And the idea here is we store all those computed inflection parameters into this MMS file, which is parsed into this idea called as MMS. And then with this also points to the signing animation in our dictionary. Next, we had this configuration, which allows us to control different bones of our skeletal animation, right? And we use this thing called as inflector with that, which basically moves the bones of our hand, of our spine, and of our everything. And using the MMS value and the inflector, we get this inflected armature. And then we pass it to the timeline composer, which will compose it into the final inflected form. Okay. So this is a very simplified diagram. And now we can see the result of the inflected animation. So first I will play back the animation. And please take a moment to observe it. So now that's played. So let's pause it and let's go to here. Wait, just hang on. So, so just here you can see that non-inflected version is completely different. Wait, again.
Could you please explain what the differences are? So
Yeah.
original sentence is what?
So this one comes from the original,
The record.
from the recording, yeah. And these one are individual, yeah, stitches, yeah,
Dictionary
yeah.
and inflected sentence, what's that?
It's the stitchery, but everything is now inflected so that it matches the original sign.
So inflected sentence and original sentence should be the same.
Yeah, exactly. Yeah, and you can see here the sign. This is the stationary, and this one is where it matches, right? Yeah, exactly. And we can also see this the same thing happening here. Like the hand motions, they're different, and they are the same
And
here.
why is the sentence nonsense?
Sorry.
Why is the sentence nonsense?
Oh, this one, the up one, or this one, this one.
No,
The-
the up.
oh,
Okay.
these are all the glosses. So the gloss,
Signers would express this in
yeah,
the sequence of signs where each sign is associated to the capitalized keyword.
so that's just an abstraction.
Sort of. Okay, so it's basically a marker for each of the signs.
Yeah, exactly. Yeah,
We could also put kind of abstract symbols.
yeah, exactly. Yes, yes,
And
yes,
stands for concept. Okay.
yes.
Okay. So in a way, the gloss is what is in the dictionary. Exactly.
Exactly. Yeah, and so yeah.
Yeah, I need to understand because otherwise,
Okay.
The non-inflected sentence, because
Yeah.
as we were playing the videos,
Yes.
I couldn't get the difference.
Uh.
And I'm saying it here, the difference, but to me, it doesn't mean anything.
Yeah, exactly. Yeah, yeah. That's the point. Because to us it doesn't mean anything, but to the viewer, it means a lot.
This is what I mean. Can you somehow explain how this a lot is so that we can understand the difference? Do you know what I mean?
Yeah, yeah, yeah. So it's like how you say a sentence, right? For us, how we can relate to the closest way is you have a sentence, and I start just adding different words together and form a sentence in normal spoken language. Will it mean anything to you? For example, I just say, "Dear school, eat me."
Ah, I see. So yeah, I understand. So it's okay. I get.
Yeah.
Yes.
Here, what happens is that the non-inflected form is just basically putting words together without.
Magic is in the inflection. The inflection glues the concept together to a whole meaning. Yeah.
Yeah.
This is what we do when we inflect words. Yeah. And this is difficult to explain this in words, but you did a great job.
Yeah. It's a good example. Yes.
Okay. Now we go on to the quantitative results. Okay. The first metric that we're going to use is joint position error. So this is like basically computing the distance between two joints so that we want to minimize it to 0. And if it's 0, then the inflected version matches the original version. And as you can see from the table, we have like 46% improvement over the non-inflected version. So, and there are these without fingers and with fingers, because we haven't inflected the fingers, which you asked earlier, right? The fingers add a lot of noise to the animation. And if you see the data, like here it's 5, and this is all in millimeters. There's 5 millimeter here, and now without fingers, this is 2 millimeter here. So all the things that we inflicted actually reduce the loss, right? However, with fingers, it's not because we haven't inflicted that one. And next, we do the same, but for the angle. The angular error is just like joint angles. And if the sign match, if the non-inflected form matches the inflected form, like if the inflected form matches the original sentence, then the error will be 0. And again, if you see here, what we received is that we gain about 30% improvement over the non-inflected version, which is still nice, right? Compared to whatever we guys having used, concatenating the animations. And finally, we have this loss, which we called as power spectrum similarity loss. And the loss, it looks a bit complicated, but the idea here is you analyze the frequency of the joint angles so that you see whether your animation is natural or not. So this loss is designed to measure if your animation looks fluid or natural or not, right? And if you compare it, so we have reduced the loss without the simply concatenated version or without the inflection. Uh, our loss with inflection is less than the one without the inflection. Nice. Now, we move on to this another figure. So here's where this gets interesting, okay? We can see, so what we did here was we inflected different body parts. So first we just inflected the hands, then we inflected the hand and head, and then we inflected hand, head, and torso, and finally hand, head, and shoulders. You can see this NPSS loss is different whenever we inflect different parts because there are certain things we didn't account for in our experiment design. Is that the hip motion controls the torso motion, right? And in turn, which controls the shoulder motion. So if you, it's like all chained together. And if one of the chain breaks, then the entire thing can break really fast. So you can see the naturalness is different for different sentences because of that reason. Then we also did some kind of preliminary user study. It's not a proper user study, so we should say preliminary user study. What we did was we invited some group of expert people, and we asked them uh, different questions. We showed them the video, right? And we asked them, how natural do you feel it? How correct is it? And do you understand it or not? And the result is something like this, where the original sentence has like around 4 scale, and the naturalness increases for our sentence. And as for understandability, there is no difference as much as compared to naturalness, and likewise for the grammar too. Okay, so after this use study, we also had a section where the users allowed to comment on why they find it so difficult, right? And this is where all the interesting part comes in. First, I'll just play the video again because this was what was shown to the user. Okay, so in the video, what happens is that there is no facial data. And as I said in the start of our talk, sign language is not about body motion and hand motion. You need the facial data. Without facial data, the signers, the native speakers, they said that there is no point in judging the animation. So this led to bad score too, right? And another reason is timing of playback. So once again, if I continue from here, you can see that the motion, these two motions, all these motions synchronize, try to synchronize together. It for us, it might look same, but to sign language people, it was too fast. It was like speaking too fast, right? Or it was the timing didn't match to what the naturalness has to be, like to the original motion. And as a result, what happened was the authors, the users who rated our study, they said that sure, your video looks natural, but it is not understandable because of the timing issues, right? Like you don't have comma, you don't have it, and there are certain abrupt motions which lead to that. And finally, I would say that there are also extreme torso movements. The reason for the extreme torso movement is I highlighted a bit earlier that we didn't have the hip motion, right? When we were capturing the sign, the whole motion capture, the authors, the captured people, they canceled all the hip motion. Now what happens is that when you cancel the hip motion, you cannot compensate for the torso motion. So you get something where your torso is prolongated forward, which can be shown somewhere around here. Right? You can see that, okay, you can see that, right? Where it just comes forward. So as I say again, so this is the timing issue, right? Here I resample the duration so that it matches the original sign. And this one is the original duration of the dictionary gloss. If I play back them together, what you will notice uh, is that this one takes a little bit longer and there's a lag from the resampled version. So what we want to do next is in future work, use the original duration instead of the resampled version. Because maybe now the user will perceive it better because they can understand it better, right? Unlike simply using the resampled version. And next, what we have is something like this kind of trajectory. So this is one trajectory for this aber, right? It's a signing motion. Now we have to optimize this kind of trajectories. How do you do that? It's a very complicated trajectory, right? And if we have such kind of motion, then our optimization fails in this kind of cases. And this is another limitation. And next, we have the problem of self collisions, where the hand penetrates the body. And the users who rated our video, they also noticed this, and they were like, "Yeah, the hand prints the body, and it shouldn't be like that. It doesn't make any sense." And they commented on this thing too. So this also affects the quality of our animation. Next, so we have some idea for the future work. So this is how a motion trajectory looks like, right? And the one in the orange, they come from human motion, and the one without the orange, these lines, they come from interpolation. Now, one thing please notice is that if you see over here, and if you draw a tangent, the tangent should continue somewhere around like this, right? But here there's a break and it just simply interpolates like that. Now that introduces all these random and shaky motions into our animation. What we would expect is we would expect this to go a little bit further and then slowly go and connect it there. But to do that is a very difficult task, and that will be led as our future work. Okay. And next is in some cases, it's really not necessary to inflect because we can see like all the animations, they look almost the same, right? Here, all of these three motions, they look identical. In this case, we can simply be like, oh yeah, in this case, you don't need the inflection. I can just avoid it completely, right? And this could also improve the fidelity. And that's for my talk. So